So we're given the problem, if 25 milliliters of 0.5 molarity NaOH neutralizes 35 milliliters of monoproic acid, what is the molarity of the acid? So in order to do this, we first use a simple equation M1V1 equals M2V2. M1 is molarity, V1 is the volume, and then M1 is the molarity of the other substance and then the volume of the other substance. So applying this to our current situation, we have now, we had to convert 25 milliliters to liters, so we get 0.025 liters. We had to convert 35 milliliters to liters, so we get 0.035 liters. And then we will now solve for N. And after you solve for M, you get the result, M equals 0.36 after multiplying these two values together and dividing by the 0.035. Now, the next problem that we have to do is to explain the chemical nomenclature. The first rule we have to explain is binary compounds of metals and nonmetals. So the rule is for those is that cations formed from metal atoms have the same number as the metal. Have the same name as the metal. For example, Na plus, which is sodium, would just have the name sodium ion. And then if a metal can form cations with different charges, the positive charge is indicated by a Roman numeral, in parentheses following the name of the element, for example, iron. You would otherwise write it as, and the 2 comes from the +2 charge here. So, and then the name of a monatomic anion is formed by replacing the ending of the name of the element with the suffix I. So if we wanted to apply this and write the chemical name of, let's say, sodium chloride, or let me say this, NaCl, it would just be sodium because of the Na, it's the cation, and then chloride. And if sodium could take on additional charges, then you would just indicate the charge of the sodium ion with the number in the parentheses, if need be. But sodium cannot form other charges other than +1. But normally this applies for metals. The second situation are polyatomic compounds made up of ionic groups. And they follow the exact same rules as binary compounds with metal and nonmetal because those are ionic as well. However, this one brings polyatomic ions into play. A polyatomic ion is a group of nonmetals bonded together that have a charge. So nitrogen is a nonmetal, hydrogen is a nonmetal. But when bonded together in a special situation, they have the charge +1. And then when this would bond with, say, chloride, then you get ammonium chloride. And the rule for the polyatomic ions can either be anions or cations, and normally they have their own name. So this is ammonia. You have such things as sulfate, as well as sulfite. The 8 in the ite is specific to the oxygen in the polyatomic ion. If the 8 refers to the most common, the most representative state of the polyatomic ion, so the O4, in nature, there's normally going to be 4 oxygens in bonded with sulfur, so that's why it gets the 8. 3 oxygens is less common, so it's 1 less than the common form, so that's why it gets the suffix ite. In other situations where there can be 4 different versions, such as in chlorate, which is ClO4, which is ClO4. This is chlorate. Then you can get, excuse me, that's a bad example. But the point is that 8 would be the most representative. 1 more than the 8 would be, you would use the prefix per, and then 1 less than ite, you would use the prefix hypo. And then the last nomenclature rule are covalent bonds. Now, covalent bonds use the prefix and suffix system, or excuse me, only prefixes, usually very intently. For example, if you were to have the compound carbon dioxide, you use the prefixes mono, and these all represent different amounts of atoms. In carbon dioxide, there are 2 oxygens, so thus the di prefix goes in front of the oxygen. Now, there's only 1 carbon, but because it's the first element, you typically leave the mono off. It's implied. Carbon, di. And the suffix of "ide" is added to the last element in the compound. And that is how you name chemical compounds.